Okay, this is quiz 4 for Math 21C. The first question reads, consider the function f of x is equal to 1 over x plus 4. The first part asks us to find the Taylor polynomial of order 2 generated by f at a equals 0, or the Taylor polynomial centered at 0. Okay, the first thing we need to do is find some derivatives of this function. The first derivative, f prime of x, is we're going to pull down that negative exponent, so we have a negative 1 over x plus 4 squared. Our second derivative is going to be f double prime of x is going to be negative 1 times negative 2 all over x plus 4 cubed. Okay, now when we plug in 0, so f of 0 is just 1 over 4. F prime of 0 is negative 1 over 16, and then f double prime of 0 is 2 over 64, which is 1 over 32. Now the Taylor polynomial of order 2 is just the Taylor series truncated after 3 terms. So our first term, so this is going to be p sub 2, the polynomial of degree 2 of x, is the first term is just 1 over 4, and then we have, and notice that's over 0 factorial times x to the 0. X to the 0 is just 1, 0 factorial is 1, so we just end up with that f of 0, which is 1/4. And then we have minus 1/16, which is over, again, 1 factorial, but that's also just 1, and then times x to the 1, which is just x. And then plus 1 over 32 over 2 factorial, that's finally something that's just 2 times x squared. So this whole thing is 1/4 minus 1/16 x plus 1/64 x squared. Okay. Part B asks us to find the Taylor series generated by f at a equals 0 and express your answer in summation notation. Okay, the first thing we need to know is what are all of our derivatives of f going to be. So if we'd continued this out, we would see that we're going to keep getting these powers of 4 in the bottom, and we're going to end up having a negative factorial. So negative 1 times negative 2, and the next term will have a negative 3, and then negative 4, and so on and so forth. So what we find out is that the nth derivative of our function f is going to be negative 1 to the n, those are from all of those negative exponents coming down, we're factoring out those negative 1s, times n factorial, those are the 1, 2, 3, we'll have a 4, 5, so on and so forth, all over x plus 4 to the n plus 1, okay? Now the way that I figure that out is I just look at the pattern. I take a few derivatives and I notice that I keep pulling down these negative exponents that are increasing by 1 every time, and that the exponent in the bottom is increasing by 1 every time. Okay, so that tells me then that the nth derivative of f at 0 is going to be negative 1 to the n factorial over, 4 to the n plus 1. Okay, so then our Taylor series, so f of x expanded as a Taylor series, runs from n equals 0 to infinity, and it's the nth derivative of f evaluated at 0, which is negative 1 to the n factorial over 4 to the n plus 1, all over n factorial times x to the n. Now this simplifies, these n factorials cancel, and we end up with the summation from n equals 0 to infinity of negative 1 to the nth over 4 to the n plus 1 times x to the nth. Okay, now problem 2 says, estimate the error if the polynomial of degree 4 is 1 plus x squared plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 is used to estimate the value of e to the x at x equals 1/3. Okay, so to start with, we know that our function is e to the x, And so we then know that any derivative, so the nth derivative of x, is also going to be e to the x. Okay, now a here is going to be 0. The way I know that is I see that there's no subtraction on the x term. Those are just x minus 0, not x minus some non-zero a. So a is going to be 0. We're centered at 0. And then our specific x value is going to be 1/3. Now, the remainder theorem says that if the n plus 1 derivative is bounded by some m for all t in our interval from a to x, the center of our polynomial, to our specific x value, then the remainder, or the error, is going to be bounded by m times x minus a to the n plus 1 over n plus 1 factorial. This is the distance, the length of our interval raised to the n plus 1 power over n plus 1 factorial times what our derivative is bounded by. Okay, so our goal here should be to find m. So now notice we know the n plus 1th derivative of f is just going to be e to the x. So we want to know what m is so that e to the x is less than or equal to m. Let's actually change that to a t. So I'm just changing the variable here. So e to the t is less than or equal to m for t in 0 to 1/3. Now e to the x, if we draw a little sketch of that function, it grows exponentially like this. It's always increasing on this in this quadrant. So from 0 to 1/3, we know the biggest it can be is e to the 1/3. So our m we're going to choose is going to be e to the 1/3. That's the biggest this derivative, which it happens to be the original function, the biggest the derivative can be is e to the 1/3, this right endpoint on our interval. Okay, so m is equal to e to the 1/3. So we then get, oh, and notice here n is 4. Let's write that up here. N is equal to 4, so we were looking at the 5th derivative of f, which still happens to be e to the x. Any derivative of e to the x is going to be e to the x, so the 5th derivative has to be e to the x. So we end up finding out that r sub 4, the error for the polynomial of degree 4 of our function, is going to be less than or equal to m, which is e to the 1/3, times x minus a. X is 1/3 minus 0, a is 0, to the n plus 1, which is 5, all over 5 factorial, which, okay, I can simplify that a little bit. That's e to the 1/3 times 1/3 to the 5th, all over 120. Okay, so we know that our error is bounded above by the maximum of the derivative, e to the 1/3, times the length of our interval, 1/3 raised to the 5th, over 5 factorial, 120.